Hello and good morning everyone. Today inshallah we will continue on vector spaces. This part is really very important. As you saw in the previous midterm, we already finished the midterm. So we will start on this part. The next midterm, midterm 2, mainly will be dedicated for the vector spaces and the rest of our course. So it's really very important to follow up as much as possible. Today I will start first making a small recap about what have been studied previously in the part of this chapter. Then I will continue with the remaining of this chapter. The problem with vector spaces, the definitions is very nice, it's direct, doesn't have plenty of complications, but the main issue is you have to understand it very well and it has to be connected together. Yesterday I have some remarks about the exam and the resolutions. I didn't start marking it yet, but within the experience of what you were writing through the exams and your questions, stuff like that, it reflects a lot of things. I will try to solve it with you later when we do a revision or something, but it raises a lot of question marks in some cases from the solutions that I saw from your companions. So I will go through it later inshallah. Okay, of course, you know all our course materials and everything, you will find them on Moodle, and also the recorded lectures, you will find them on YouTube. I want to signify that if the attendance is less than 50%, the recorded lectures are not going to be raised on the YouTube. Till all of you attend the lectures regularly, okay? The recorded sessions is not a replacement from your attendance in our lectures. You have to attend the lectures and then to review from the recorded versions if you have questions, okay? Okay, let's start with the vector spaces continuation. First of all, a small recap, what's a vector space? A vector space, it's a set, non-empty set. It's really very important to understand the meaning. It's a non-empty set of not just only vectors. It may be vectors, it may be matrices, it may be polynomials, it may be objects, it may be functions. So it's a selection of objects all together, okay? It's not empty set. And it has two main things or two main major properties you have to put in mind. Addition closure and the multiplication by scalar closure. And these 2 points are really essential in the definition of a linear vector spaces, okay? So we will start by the addition closure. What's the meaning of addition closure, Muhammad? It means if you have a vector u, we will use vectors as an example in most of our cases, okay? Because it matches all the contrast of the lecture. So mainly if you have u and v, two vectors belongs to this vector space, this selection of vectors. Their addition must belong to this set. So their addition should belong to this set. This is what's meant by addition closure. So if you have any two vectors in this room, the sum of them will exist in this room. That's the meaning of a vector space. Number 2, you have this associability. You have the commutativity, which means u plus v is equal to v plus u. You have the existence of the null, which is really very important, a null vector, which means the zero of the addition properties, so which is already exists in this set. Also, the existence of the symmetry or negation or the inverse of the addition vector, which simply means if you have a vector 1, 1, 1 in this room, you should have negative 1, negative 1, negative 1 also exist in this room. So once you add them together, the result will be the origin, okay? That's the requirements for the addition. The requirements for the multiplication by scalar, any vector belongs to this room. If you multiply, look to the definition, listen to the definition. If you multiply this vector by any number, can you imagine any number from negative infinity to positive infinity, the result will exist in this room. Can you imagine how bigger this set is? Okay, so this is the main definition. So you have the multiplication by scalar associability, and you have the distributivity of either a scalar on two vectors or two scalars or one vector, and the existence of the multiplication identity, which is 1. All of this, I can short them up. An addition closure and the multiplication by scalar closure. Just two things. All the remaining 5 probabilities, it's related to addition or related to the multiplication by scalar. Once you have a vector space, the following is its an advantages. It should exist in this vector space. Once you define this room to be a vector space. Number 1, it will have an origin. Once you multiply any scalar by the origin, the result will be the origin of this vector space. Also, the zero of any vector is the zero of this vector space. -1 times v is going to be negative v, which is existence, the symmetry of any vector. A times v equal to 0 of the vector space, it means, it implies either one of two things. Either A is equal to 0 or the v vector is the null vector. Those are, by the definition, should exist in this room, which is called the vector space. Okay, what's a sub-vector space? So imagine the vector space is like the room that we are in. A sub-vector space is a part from this room, okay? But this part from this room should at least contain the origin of this room. So if we imagine that this is the origin, so a sub-vector space will be a box around this origin within the space of this room. That's a sub-vector space, okay? Okay, the sub-vector space by itself is considered a vector space. Every sub-vector space from this room by itself, it's supposed to be a vector space. Why? Because it has an addition closure and the multiplication closure by itself. So every sub-vector space is a vector space by itself. Why we call it a sub-vector space from a vector space? Because they share the same origin and it is part of it. Okay, so the conditions for a sub-vector space, number 1, the origin of the main vector space should belong to this sub-vector space. Number 2, addition closure. Number 3, multiplication by scalar closure. So this means a vector subspace of a vector space is a vector space. The definition that I told you about. And also, every vector space is a vector subspace of itself. The two definitions make sense, make a complete sense. The requirements already exist and everything. Now we finished what's a vector space and what's a sub-vector space from a certain vector space. Now we will move to the new definitions or the new relations of today. Omar, please try to concentrate. We will try to work now on 3 main relations that will affect the relations between sub-vector spaces. So imagine we are talking about this room. Then we consider the sub-vector space. Now we are going to join or to union or to add 2 sub-vector spaces in this room together. So we will talk about intersection, union, and the sum of sub-vector spaces or subspaces, okay? The word subspaces, it's exactly like sub-vector spaces, okay? Okay, what's the intersection, what's the union, and what's the addition? In linear algebra, the concept of intersection, union, and set addition are related operation performed on sets. First of all, the intersection. If I have A, a sub-vector space, and B is another vector subspace, the intersection of both of them, means the vectors that exist in both A and B. So the joined vectors between these 2 sub-vector spaces. Okay, this is what's meant by intersection. Of course, the intersection definition is given. The section of 2 sets A intersection B is the set of all elements of vectors that are both in A and B simultaneously. The intersection is a set of vectors that are shared by both A and B, and if A and B are vector subspaces, the intersection is also a sub-vector space. Why the intersection is a must be a sub-vector space? Why? Because each sub-vector space, each one of these sub-vector spaces belong to this vector space, will contain at least the origin, am I right? So first of all, they have the origin, okay? And then the elements shared between both of them will satisfy the addition and the multiplication by scalar. So the intersection between two subvector spaces will develop either a set of vectors or the origin, at least the origin, okay? So in either cases, it will have a subvector space. This is really very important. Okay. Always produce a subset of both A and B. We already covered this issue. The intersection can be empty if there are no common element or vectors between these two subsets. And example. Look to this example. We have A, which is a set containing 1, 0, 2, and 0. And of course, this is, we will know down the road today, that's if it is a basis for this subvector space. So these two vectors should generate all the vectors belongs to this subvector space. So if I have 1 and 0, 2 and 0, and B, if this is 1, 0, 3 and 0, the intersection will mean the vector 1 and 0, or the set 1 and 0. Are you with me, Mr. Muhammad? Which is the vector that exists on both of them. Of course, the definition will be slightly different by the end of this lecture. Okay? Now I will talk about the addition of subvector spaces. The addition of subvector spaces, it means you will add the identity of this subvector space to another subvector space. Usually the addition will change the nature of the elements belongs to a certain subvector space. Okay, in addition, set the addition is the context of the usually refers to addition of two sets of vectors, often vector space or subvector space. So the intersection will develop, if it was between subvector spaces, it will also develop a subvector space. If I'm talking about A plus B, adding these two subvector spaces, the results will be vectors that's sharing A small from A capital and B small from B capital, which means it will share vectors from A plus vectors from B. That's the addition process. Example, and it will be very obvious for you. If I have the set of 1 and 0, okay, and this is a subvector space, which means A times 1 and 0. So the elements like 1 and 0, 2 and 0, negative 1 and 0, 3 and 0, 4 and 0, negative 4 and 0, negative 5 and 0, which is the x-axis, okay? And if I have 0 and 1, and this is, it's gonna be 0 and 1, 0 and 2, 0, 3, 0 minus 1, 0 minus 2, okay? That's the whole set. If you add them together, the result will be 1 and 1, which means all the elements which have 1 and 1, which is a subvector space. Because 1 and 1, if you multiply it by A, and A belongs to R, if A is equal to 0, you will have your origin. If A is positive, if A is negative, you will have the elements. Remark, Mr. Muhammad, that's the shape of the vectors, that's the shape of the vectors in A. That's the shape of vectors in B. So that's the x-axis, that's the y-axis. When you add them together, you will be able to have the first part or the first quartile, which stands for 1 and 1, or the elements in the first quartile proving 1 and 1, which is a straight line passing through the origin. Are you with me? So that's the addition. Okay, now I know the intersection, only the shared elements, okay, before we go to another problem, what's the intersection here between this set and that set? What's the intersection between this set and that set? Origin. The origin. Yes, you are right. Because I'm talking about the x-axis and I'm talking about the y-axis, so the intersection will be only the origin. Okay, what if I am having the union of these two vectors? If I'm having the union of these two vectors, I will have also, okay, as a partially all the points of the vectors on the x-axis plus all the points on the y-axis, but not the addition of both of them. So I usually like to give this example. If I have 1 and 0 and 0 and 1, I'm talking about the set of 1 and 0. And this set or this generating system or this basis, it's a generation for the x-axis. The basis or the set of 0 and 1, I'm sorry, I'm borrowing this definition, we will have it by the end of today's lecture. Okay, I'm talking about all the points on the y-axis. If I'm talking about the intersection between them will be just only O and O, which is the origin, which is considered the subvector space by itself, because it contains 0 by itself, and also this origin, if you multiply in any scalar, the result will be the origin, which exists in itself. If you add two vectors 0, 0 to 0, 0, the result will be 0, 0, and also it's a minor or trivial subvector space. Okay, that's for the intersection. If I'm talking about the addition, so I will add these two elements, Ya Omar. If I added these two elements, I will be considering the set of vectors with basis 1 and 1, which is gonna be represented by a 45 straight line. All the points on this straight line, it represents, okay, A plus B. So if this is A and that is B, A intersection B will be the origin. If I'm talking about A plus B, I will be talking about the set with 1 and 1, which means all the points on this line, which represent a subvector space. But if I'm talking about A union B, I'm talking just only about the set of the points 1 and 0 and the 0 and 1, without a linear combination between them. And also the definition is borrowed from by the end of this lecture. Okay? So I will have only the set of the elements that belongs to the x-axis and the set of elements that belongs to the y-axis. Both of them together. When you think about this, you may ask me, okay, I have now the x-axis, all points, and the y-axis, all points. Doesn't this or this subvector space or this set represent a subvector space? If I have all the points on the x-axis and all the points on the y-axis, is this set represent subvector space? ليه? First of all, it has the origin. Am I right? The origin will be involved. But the problem is, it doesn't have an addition closure. If you have the point 1 and 0, and you have the point 0 and 1, and added them together, you will have 1 and 1. And the 1 and 1 doesn't belong to this set. Do you read me, Muhammad? So it's a failure in the addition, okay? So, although the intersection and the addition are both subvector spaces, the union in this case is not a subvector space. The union will be a subvector space in just only one case, if A is a subset from B or B is a subset from A. Other than that, it's not gonna be. Okay, I believe this example is very obvious, and also I've talked about the union of two sets that you are going to have exactly as I told you, that for this example, exactly like A, 0, 1 and 0, and the 0 and 1, if you have the union, you will have the elements on this shape, and you will have this element is not going to belong to this set, and so you will have a failure in the addition. This is a very, very important concept in intersection, union, and addition. The PDF I sent earlier for you, it contains a detailed comparison between the intersection, union, and the addition of subvector spaces. So you already have this slide. I don't want to lose time in reading it with you, okay? But it is containing all the comparison or the required comparison between all of them. The definition, the operation, the results, the resulting sets, the subspaces, the closure under addition, and everything. Okay, now I want to back to the main slides. Our slides from this one, it contains the intersection, of course, which means it's defined, as we already know, as the vectors shared by V and U, okay? The sum of vectors, which means that we have a combined vector, which has its two components relative to the two subvector spaces. There is what's called the direct sum. What's a direct sum between two subvector spaces? If the intersection between two subvector spaces just only the origin, and every vector in this subvector space consists of a vector from the first subvector space and apart from the second subvector space, it's called the direct sum. So what's the direct sum? The direct sum is a new subvector space, okay? Performed, or you will have it from adding two subvector spaces, but under one condition. The intersection of these two subvector spaces is just only the origin. And each vector in the result, which is the direct sum, is consisting of a unique value between the vector from the first subvector space and the vector from the second subvector space. That's the definition of direct sum. And also it can be generalized. Let's look to this example. We need an example to show how to get the relations. Consider the subspaces. Okay? خليك معايا يا عمر، انت مش معايا. والامتحان بتاع امبارح كان موضح بعض اسئله كلها دليل ان انت مش مركز كفايه.
لا والله.
ماشي. Consider the subspaces of R3. بيقول لك U، خلي بالك بقى، ركز شويه. بيقول U is a subvector space of the elements X, Y, and Z, which belongs to R3, but just only the elements with X minus Y equal to 0. يعني ايه يا محمد X minus Y equal to 0؟ يعني انا هتكلم على الاليمنتس in R3 بس اللي فيهم الاكس بيساوي مين؟ الواي. يعني شكل الاليمنت، يعني اقدر اقول ده على فكره each subvector space can be given to you. Each subvector space can be given to you in either two ways يا عمر. One of them is the equation type, and the other type of definition is by the span. What's the span? The generating vector of this subvector space. So look at me step by step. I can put this subvector space, which is U, which can be expressed as the set of all X, Y, and Z. So the elements X, Y, and Z, which belongs to R3, such that all the X values equal to the Y values. This definition exactly like this one, which means, Mr. Omar, إن أنا عندي Y, and Z, and that's the special case from R3. Do you really understand what's written? What's written? X, Y, and Z. It means a point. Okay, just a second. A point or a vector in the 3 dimension where X is changing from negative infinity to positive infinity. Y is it changing from negative infinity to positive infinity. And the Z is it changing from negative infinity to positive infinity. Okay? With no relation connecting them. Okay? So I can have the point or the vector minus 1,000, 10,000, and 0. Or I can have 5 minus 100 plus 10,000. Do you read what I'm saying? So the X is changing, the Y is changing, this is changing, there is no control. Out of this set, من الست ده أنا بتكلم على specific subvector space، يعني specific set. الست دي يحصل فيها إيه؟ يحصل فيها إن ال Y belongs to R3 بس just only the two values of X and Y equal to each other. You read what I'm saying? And the Z is free. So the set of these points، تاني كمان مرة يا عمر أنا هشيل منك موبايلك. ده معناه 0 0 مثلا 0 0 1 1 1 و 5 negative 1,000 negative 1,000 200. The first two components will be equal to each other and belongs to the real set. But the third one is moving, is free. This set that I'm giving to you, that's the formulation of this set. I can express it by another way. Okay? By expressing this set in the following form. Look to this form. Y and 0 plus 0 0 and Z. Look to this relation. Y 0, then 0 0 and the third component is Z. If you add these two components together, you will get Y Z. Also, I can take Y as a common. So I will have 1, 1 and 0. And also I can take Z as a common, so I will have 0, 0 and 1. And in such case, you have Y and Z belongs to the real set. This is U. I can establish now what's called a span for U, which is 1, 1 and 0 with the vector 0, 0 and 1. It will be defined also just in a few minutes. So I can give you any subvector space, Mr. Omar, by two things. Either an equation type, like what you saw, or a span type. What's the span type? This 4. It was like the previous example, 1, 0, 0, 1. Okay? So it's simply 1, 1, 0 plus 0, 0, 1. And I can form all the elements on this case. Okay, if you look to the other set, the other set also is a subvector space from R3, but under the condition that every Z is equal to 2 over Y. So I have two subvector spaces. One of them, it has a minor condition that the X and Y components are equal to each other. And the second one, it has an opinion that the third component is twice the second component. Am I right? So simply, if you make the substitution, that's the first set. The second set, which is W, I can put it this form, that W is equal to X, Y, and, okay, 2 over Y, which is a set out of R3. If you look to both of them, this set is a subvector space from R3 for all the points where the first and second components are equal to each other. This set is also apart from R3, but those numbers where the third component is twice the second. Do you read me? This is how you form your subvector space. If I'm talking about the intersection, I'm talking about the set which had the two conditions together. Which has the two conditions together. You have to satisfy both conditions. That's what's meant by intersection. So if I'm having, if I'm having U intersection W, if I have U intersection W, I will be talking about the set of points X, Y, and Z, which must obey that X minus Y is equal to 0, and also obey that 2Y minus Z is equal to 0. So I will need the elements combined between these two conditions. How to form them? I will look to these two relations. First of all, X is equal to Y. So I'm talking about Y and Z. And on the same setting, I have that Z is equal to twice of the values of Y, which means Z is equal to 2Y. That's the shape of the set of U intersection W. That's the new set, which is connect both the condition for the first subvector space and the conditions for the second vector space. Are you with me? So, تاني الأولانية كان فيها شرط إن the first two components equal to each other. التانية كان فيها شرط إن the third component ضعف second component. Okay? لما combine them together لازم الconditions دي كلها تتحقق مع بعضها. Okay? So I'm talking about the set which have the following. This is the condition from the first subvector space. That's the condition from the second subvector space. So they have both to be applied. So y is equal to x and z is equal to 2x or vice versa. Now I will have the form of this vector space, which is gonna be 1, 1, and 2. Usually, Jose likes to write the zeros plus constant times 1, 1, and t. I usually like to write it this way: 1, 1, and 2 times y, and y belongs to r. This is actually contain the definition of the given one. So this definition is exactly the same as this one. Because the meaning is, it's a stress, this definition, stressing on the fact that the origin already exists in this subvector space. Am I right? It is already exist. Why it is already exist? Because y belongs to mean to r. And one of the numbers of r is 0. So if you put y is equal to 0, you will have the 0 in front of you. So I don't have to. But it is written this way. So either you write it this way or that way, both of them is correct. Are you with me? Any questions? So what is the intersection? Is to obey both conditions. So this problem is really very nice one. It shows you how to bring, to find the definition. He's asking you also to consider the subspaces of R3, which is x00, stand for the points on the x-axis, or the vectors of the x-axis form. And for the points with 0, y, and y, which means it's about from R3, that the first component must be 0, and the second and third components are equal to each other. Okay, you want these subvector spaces to be added together. If I'm adding these two vector spaces together, what's gonna be the result? The result will be x plus y and y, okay? So if you add them together, the result will be this vector plus the condition from the other vector. Once you add them together, you will have a new set. The new set will be x, y, and y. That's the new set. Where x and y belongs to r. And also it is written in a form of an equation. If I want to write it in the span form, we will see it down the road. Okay, I will get back to this slide later. Okay, شباب? حركوا معايا? Okay, perfect. So that's the final. And it's a plan, it's okay. Of course, for those two subvector spaces, if you look to the intersection between these two subvector spaces, x belongs to r, y belongs to r, this is x00, that's 2y and 0, there is no combination between them, there is no combined condition between them. So the intersection will be just only the origin. Are you with me? This is why we have the intersection. As you saw, it is just only the origin. Subvector spaces U and V is a subvector space. As I told you, that's the condition for the union. Okay, now for a very important definition. That's a generalization for the direct sum. I'm sorry. That's a direct definition of the direct sum. If you remember the direct sum, if you have two subvector spaces, the intersection between them is 0. So their addition, you will have to add the first plus the second, both together, and it's done. I can generalize this for 3 or 4 vector subvector spaces if the intersections are 0, so you can add them all together. Okay. Now I'm going to talk about a very important part of vector spaces and vector subvector and subvector spaces, which is the linear combination, and it is related to the addition of vectors and how to express certain vector space as a generating set of vectors. This part is really very important. It's called talking about linear combination, spanning the sets that I was going to give you in the previous example, and the basis of a certain set. Those are key definitions in the chapter of vector spaces. Let's start with the linear combination. Okay, the linear combination is this relation, which simply states that any vector u can be generated from another set of vectors by multiplying the first vector by alpha 1, multiplying the second vector by alpha 2, and so on till you reach the alpha n, u, n, or whatever. Which means I can generate vectors from each other. This is really a very important definition. The linear combination. It means if I have 3 vectors, I can generate a 4th vector out of them. How to form it? By multiplying each one of these vectors by a constant and adding them together. One of the simplest methods or the simplest vectors which is proving the linear combination is, for example, the vector, let's say, the vector 3, 5, and 6. I can express, first of all, this vector belongs to the set of R2 or R3 or R4, Mr. Omar? This vector, 3, 5, 6.
R3.
R3, why R3?
3 rows.
It has 3 components, okay? I can express it as a linear combination of the standard vectors of R3. Very simple. By doing this, considering alpha 1 is 3 times 1 double 0, then alpha 2 is 5 times 0, 1 and 0, then 6 times 0, 0 and 1. So now simply, I can define the vector 3, 5 and 6 as a linear combination of how many vectors? 3. What are the 3 vectors? The standard set of vectors, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. Sometimes we call them the canonical basis. So that's a proof that for every vector space, if V be a vector space, U1 and UR be a finite family of vectors of F. Once more, R3 or V is a vector space which has U1, U2, U3, 3 vectors, belongs to this family, okay, for R3. Then, and the alpha 1, alpha R be scalars. It's exactly like 3, 5 and 6, which are scalars. I can get this vector on this form, alpha 1 U1 plus alpha 2 U2 plus alpha 3 U3, according to the number of these vectors. Okay? That's the linear combination. If you remark, this linear combination, it's measured in the previous examples that we have. I will back to it, but after finishing this part. Okay, now, it is called the linear combination. So this equation is called the linear combination of vectors U1 up to UR with coefficients alpha 1 up to alpha R. That's the equation. Any vector I can generate by simply multiplying alpha 1 U1, alpha 2 U2, and so on. That's the linear combination. 3 to 0, the vector 3 to 0. I can express it as 3 times 2 times 0 times the linear combination. So these are called the standard or canonical basis, which is 1, 0, 0, 0, 1, and 0, 0, 0, 1.